Hey everyone, today we're going to talk about something that's literally all around us. The basic ideas that make our entire digital world tick. I'm talking about the music you stream, the calls you make, everything. It all comes down to a few surprisingly simple building blocks. So let's dive right in.
So think about it. Every single thing you see or hear on a screen, on your phone, whatever, it's all just signals. But what are they saying? What's the hidden language they're all speaking to each other? Well, we're about to crack that code. And you know what? It's way simpler and honestly more elegant than you probably imagine.
All right, first things first. Before we get into the nitty-gritty, we have to lock down one single, absolutely essential rule. This is the foundation for everything else we're going to cover. Think of it as the master blueprint. Okay, look at this. It seems super basic, but trust me, this is the core idea. On one side, you've got a function, let's call it g of t. It's just a shape plotted against time. On the other side, it's g of alpha. But here's the thing. Notice the shape? It's exactly the same. This is so important. A function's real identity, its soul, is its shape. The letter in the little brackets, that's just a label. It's a placeholder. It doesn't matter if it's t for time or x for space or alpha for whatever. The shape is the blueprint. Get this, and you've got the key to everything else. Okay, so now that we have that blueprint rule down, it's time to open up our toolkit. And here's the cool part. To build or break down pretty much any signal you can think of, you really only need to get your head around three basic functions. These are your essential tools. First up, we have the delta function. This thing is like a surgical laser. It's our tool for absolute pinpoint precision. Imagine you want to grab something that happens at one single exact moment in time. That is what the delta function is for. It's this perfect, infinitely tall, infinitely thin spike at one spot and then nothing. Zero everywhere else. It's the ultimate tool for isolating one single point in time or space. Next in the toolbox is the step function. And really, it's just a switch. This simplest switch you can possibly imagine. It's just off, off, off. Its value is 0, and then boom. At one specific moment, it flips on to a value of 1 and just stays there forever. This is our go-to tool anytime we need to model something turning on.
And last but not least, we've got our third essential tool, or I guess tool set, sine and cosine waves. These are, well, they're the fundamental language of anything that repeats or oscillates. A pure musical note, a radio wave, the hum of a power line. It's all built from sines and cosines. The only real difference between them is where they start. A cosine wave starts at its highest point, at 1. A sine wave starts in the middle, at 0. That's it. Together, they are the literal DNA of anything that has a cycle.
All right, so we've got our tools, we've got the blueprint. Now let's put them to work. We're going to start with our most precise tool, that delta function, and look at two incredibly powerful things it can do. This first trick is called the sampling property, and I'm not exaggerating when I say this is the idea behind pretty much all modern digital technology. Think about it. How do you turn a real-world continuous sound wave into a bunch of numbers on a computer? You have to measure it, right? You have to take little snapshots of its value at specific moments. Well, multiplying that signal by a delta function, that's how you take the snapshot. It perfectly grabs the value of the signal at that one single instantaneous point. So let's break that down. How does it actually work? Imagine you've got some signal, call it x of t, just wiggling along through time. Now, we bring in a delta function that only exists at one exact moment, say at time equals 2. When you multiply them together, what happens? Well, since the delta is 0 everywhere but at 2, the result is also 0 everywhere else. The only thing that survives is the value of the signal at that one point. So what you're left with is a new little spike, a new delta function, whose height is exactly the value of the original signal at time equals 2. That's sampling. That's the whole magic trick right there. Okay, so trick number 2 for the delta function is shifting. This uses a fancy-sounding math operation called convolution. Don't let the name scare you. For our purposes, just think of it as a special kind of sliding and multiplying process. And here's the amazing part. If you convolve any signal, any shape, with a delta function, you just pick up that entire shape and slide it over, perfectly intact, to wherever the delta function was. The shape doesn't change a bit. You just moved it in time. Okay, now it's time to bring out the heavy machinery, the power tool in our kit. So far, we've only been looking at signals as they unfold over time. But what if we wanted to see what they're made of? What are their ingredients? To do that, we need something called the Fourier transform. This is our secret decoder ring for signals. The best way to think about the Fourier transform is like a prism. You know, you shine white light through a prism and out the other side comes a rainbow. all the different colors or frequencies that were hiding inside that white light. Well, the Fourier transform does exactly that, but for signals. It takes any complex signal you give it, and it spits out the perfect recipe. It tells you exactly which sine and cosine waves make up that signal, and how much of each you need. It literally reveals the signal's frequency DNA. And here's a classic example. On one side, we're looking at things in the time domain, the way we normally experience them, and we see a super simple signal, a square pulse. It's off, then it's on for a bit, then it's off again. Simple, right? Well, not really, because when we run it through our Fourier prism and look at it in the frequency domain, we get this totally different shape. What this is telling us is that to build that simple square pulse, you actually need an infinite number of different frequencies, all added together. Mostly low frequencies, but a little bit of a whole bunch of higher ones too. Okay, now let's play with this a bit. Let's explore a really cool fundamental property. What if we take that square pulse and we just stretch it out, make it wider in time, so it's a slower, longer event? What do you think happens to its frequency recipe? It contracts. It gets narrower. A signal that is wide and slow in the time domain becomes skinny and compact in the frequency domain. And the reverse is true too. A fast, sharp signal in time is very wide in frequency. This is a basic trade-off baked into the universe. Slower, simpler signals need less frequency real estate, which is what we call bandwidth. Faster, more complex signals need a lot more bandwidth. It's a trade-off you can't escape. So when we talk about frequency, we're really speaking two different dialects or two languages. There's F, which is measured in hertz. That's the intuitive one. It's just cycles per second. How many times does the wave go up and down in 1 second? Easy. Then there's the other one, angular frequency, which we write with a capital omega. This one is used because it just makes all the math work out much more cleanly. And this little equation right here, it's our Rosetta Stone. It's the universal translator that lets us switch back and forth between the easy-to-understand physical world and the world of clean mathematics. Okay, we've got our blueprint, we've got our basic tools, and we've got our power tool, the frequency decoder. Now, let's go into the workshop and put it all together. Let's see how these concepts actually explain how a real-world thing, like a filter in an audio system, actually works. So we're going to focus on a really common but special kind of system. It's called an LTI system, which stands for linear time invariant. You can just think of it as a black box. A signal goes in one side, the box does something to it, and a modified signal comes out the other side. And the most important thing to know is that the mathematical operation this box performs is convolution. Yep, that same sliding and multiplying thing we saw the delta function do. And this right here is the golden rule. This is the whole reason we bother with the Fourier transform. That complicated, kind of messy convolution operation you have to do in the time domain, well, in the frequency domain, it becomes simple multiplication. You just multiply two numbers together. This is a huge deal. It's what makes the Fourier transform the ultimate cheat code for engineers. It takes something really hard and turns it into something really, really easy. And that golden rule leads us to maybe the single most important takeaway about these systems. Here it is. If you feed a pure sine wave into an LTI system, a pure musical note into a guitar pedal, for example, what comes out is a sine wave at the exact same frequency. The pitch doesn't change. The system can make it louder or quieter. It can shift it a little, but it absolutely cannot create new frequencies that weren't already there. So why is that? Let's connect all the dots we've laid out. Remember what a pure sine or cosine wave looks like in the frequency domain? It's just a couple of perfect delta spikes. And what does the system do in the frequency domain? It just multiplies. So the system's frequency response just multiplies the height of those spikes. It can make them taller or shorter, changing the amplitude, but it has no power to move them to a different frequency. It's just scaling their values, not changing their location. So there you have it, the secret language of our digital world. Turns out it's not so secret or complicated after all. It really just comes down to a few simple parts: a perfect spike, a simple switch, and a basic wave. And a few key rules that let us see how they all fit together. Every complex sound, every image, every piece of data flying through the air is built from this incredibly simple toolkit. So it kind of leaves you with a final thought, right? As you're listening to this, as you're looking at your phone, what other complex signals and systems are you interacting with right now that are all built from these same essential building blocks?